You wake up tomorrow and every single computer on Earth has vanished. Your phone is a useless brick. Your car won't start. The internet is gone. Bank accounts, social media, your entire digital life just erased. Now here's the terrifying part. The mathematical principles that made all of this possible were invented over 1,000 years ago by a Persian scholar in Baghdad who was just trying to figure out how to divide dead people's property. Yeah, I'm serious. So before we dive into how a medieval mathematician accidentally created the foundation of every technology that's probably tracking you right now, smash that like button if you want your mind blown, and drop a comment telling me where you're watching from. Seriously, I read them. Now grab your favorite drink, dim those harsh overhead lights, put your phone on silent, ironically enough, and let's travel back to 9th century Baghdad, where everything changed. You're walking through the dusty streets of Baghdad in the year 820. The air smells like cardamom, burning oil lamps, and something you can't quite identify but definitely wouldn't smell in Brooklyn. Merchants are screaming in Arabic, Persian, Hindi, Greek, and probably 12 other languages you don't recognize. Donkeys are loaded with silk, spices, and papyrus scrolls. It's chaotic and loud and smells like every animal in existence decided to have a very productive day, but you're not here for the spice market. You're heading to the most advanced research facility on the planet. As you push through the heavy wooden doors, the noise of the street fades away like someone just hit mute on reality. Inside is something from another world. Hundreds of scholars bent over manuscripts, their fingers stained black with ink. The walls are absolutely covered with texts in Greek, Sanskrit, Persian, Syriac, Arabic. This isn't just a library, this is humanity's first think tank. And right now, a young Persian mathematician named Muhammad ibn Musa al-Khwarizmi is about to invent something that will change the course of human history. He doesn't know it yet. He's just trying to solve a really annoying problem. Al-Khwarizmi has a problem, and it's not the kind you can ignore. People keep showing up at the House of Wisdom with inheritance disputes. Dad died and left 17 camels to his 3 sons, but the will says the eldest son gets 1/2 of the estate, the middle son gets 1/3, and the youngest son gets 1/9. Try doing that math. Go ahead. I'll wait. You can't just cut the camels with a sword, because then everybody gets dead camels and that defeats the purpose of inheritance. In Europe right now, they're using Roman numerals, which means you'd be writing this as MCDCCKSL divided by CCC, or something equally horrifying. These weren't just math puzzles, these were real legal cases, real families, real money, real problems that needed solving fast. So al-Khwarizmi does something extraordinary. Instead of solving each inheritance problem individually, like some kind of mathematical therapist, he starts looking for patterns. He begins developing systematic methods, not just answers but procedures, step-by-step instructions that could solve entire categories of problems. He doesn't call them algorithms yet. That word doesn't exist. He just calls it the method. His book is titled Kitab al-Jabr wala Muqabala, which loosely translates to the Book of Restoration and Balancing. That word al-Jabr, that's where we get the word algebra from. But here's what's absolutely wild about this muse. He wasn't even trying to invent computer science. He was just tired of doing the same calculations over and over. You flip through his manuscript, and something feels off. Where are all the symbols? The X's and Y's and plus signs and equal signs that made high school algebra feel like torture. They don't exist yet. Al-Khwarizmi is writing everything out in words, full sentences, complete paragraphs. Imagine solving quadratic equations using only sentences. Try explaining the Pythagorean theorem without any symbols. It's like trying to code an app using only Microsoft Word. But that's exactly what makes his work so incredible, and also kind of incredible to read. He's creating something revolutionary that we now call an algorithm, using nothing but language and logic. Think about what an algorithm really is underneath all the jargon. It's a recipe, a set of instructions so clear and precise that anyone can follow them and get the same result every single time. When you type something into Google, billions of algorithms are running. When Netflix recommends yet another true crime documentary that you absolutely will watch at 2 in the morning, that's algorithms. When your phone unlocks with your face, when your car drives itself, when AI generates that weird picture you asked it to make, algorithms. But the concept itself, the very idea that you could take a complex problem and break it down into simple, repeatable, mechanical steps, that idea started right here with a guy trying to figure out how to split up camels fairly. Now you might be thinking, okay, one smart guy figured out some math tricks. Big whoop. But al-Khwarizmi wasn't working alone in some tower muttering to himself. He was part of something extraordinary. The House of Wisdom wasn't just another library. It was Silicon Valley, MIT, the Library of Alexandria, and a research university all rolled into one building with way better weather. Scholars from India brought the decimal number system. Mathematicians from Greece and Persia were translating ancient texts and finding mistakes in them. Chinese inventors' work was being studied and improved upon. Persian astronomers were calculating planetary orbits. This wasn't just multiculturalism as a nice idea. This was intellectual fusion at a level the world had never seen before, and honestly might never see again. The Caliph al-Ma'mun, who funded all of this magnificence, was basically the Elon Musk of the 9th century. Except he was smarter and didn't have Twitter. He was obsessed with knowledge, the way some people are obsessed with TikTok, but infinitely more productive. Legend says he had a dream where Aristotle appeared to him and they had an actual philosophical debate. When he woke up, he decided that he needed to collect every single piece of human knowledge ever written and bring it to Baghdad. So he sent delegations all across the known world, to Byzantium, to India, to Central Asia, to China, offering literally tons of gold for manuscripts. Imagine if Bezos decided that instead of trying to go to space, he was going to download all of human intelligence into one city. That's al-Ma'mun. That's what he did. You watch as scribes carefully copy texts, but they're not just copying like mindless robots, they're actually improving them. When they find an error in Ptolemy's description of astronomy, they fix it and note the correction. When Greek geometry seems incomplete or wrong, they expand it and make it better. When Indian numerals meet Arab linguistics and Persian mathematics, they create new notations that combine the best of everything. This isn't just preservation of knowledge. This is active evolution. This is standing on the shoulders of giants, and then climbing a ladder to get even higher. Every improvement, every innovation, every small breakthrough gets copied and sent to libraries and universities and research centers from Cordoba in Spain, all the way to Samarkand in Central Asia. There's a network of knowledge flowing through the Islamic world, and it's accelerating. Scholars are writing letters to each other, arguing about proofs. They're sending their newest work to be reviewed by other experts. They're building on each other's discoveries. It's collaborative science 800 years before collaboration became fashionable. But here's where it gets really interesting and kind of explains why Islamic scholars became so obsessed with systematic thinking and computation. They had a religious motivation that accidentally pushed them toward the foundations of computer science. See, Muslims need to pray 5 times a day, facing Mecca. But how do you figure out which direction Mecca is from Cordoba, or from Cairo, or from some random village in Central Asia? And how do you know exactly when to pray when you're traveling, and your normal schedule is all messed up. These aren't simple problems. You need spherical trigonometry, you need accurate timekeeping, you need complex calculations that need to work precisely, or the whole religious obligation falls apart. So Muslim mathematicians developed increasingly sophisticated computational methods. They created tools and techniques and procedures that could process information in a systematic way. They were basically building analog computers out of pure mathematics and geometry. Let me absolutely blow your mind right now. The word algorithm itself comes directly from the Latinized version of al-Khwarizmi's name. When scholars in medieval Europe encountered his works, they called them the al-khwarizmi. Al-khwarizmi became algorithm. Every single time a programmer anywhere writes an algorithm, they are literally invoking the name of a 9th century Persian scholar. Your iPhone runs on mathematical principles developed by a guy who never saw electricity. A computer that fits in your pocket uses logic created by someone who thought the Earth was the center of the universe. The artificial intelligence that's probably going to make your job obsolete in the next decade, its fundamental logical structure was worked out by scholars in medieval Persia. You spend a full day in the House of Wisdom watching these scholars work, and you start to notice something that separates them from other intelligent people throughout history. These scholars are obsessed with being systematic. They document everything. They peer review each other's work. They check for errors. They build on previous discoveries intentionally and carefully. They create standardized terminology, so everyone's using the same words to mean the same things. They develop proof methods to validate new ideas. They're not just doing science as a hobby. They're creating the scientific method itself, while also accidentally creating the foundation of computing. And at the absolute center of all of this is one revolutionary idea that changes everything. That idea is that human reasoning can be broken down into steps, that thinking itself can be mechanical, that thought could become algorithmic. You wake up on day 2 of your medieval adventure, and the sun is just starting to hit the minarets outside. The city is already waking up. Merchants are setting up their stalls. Scholars are streaming into the House of Wisdom with scrolls and tablets. You've got coffee, or rather you've got kolwa, which is basically medieval coffee and tastes incredibly strong and bitter and wonderful. Now here's where things get really interesting, because we need to talk about the people al-Khwarizmi was working with. See, al-Khwarizmi didn't invent algorithms in a vacuum. He was part of a crew, a team of absolute geniuses who were all working on similar problems from different angles. And if you want to understand how algorithms were really born, you need to understand these people. First person on our list is al-Khwarizmi, and this dude was basically Batman. If Batman was really into cryptography and lived in Baghdad. Born around 801, he didn't just study mathematics, because why would you limit yourself like that? He studied philosophy, medicine, music theory, chemistry, logic, astronomy, and about 40 other subjects. But his superpower was hidden. His real party trick was inventing something called frequency analysis. You know how in spy movies, the nerdy character breaks an enemy code by noticing which letters appear most often. Al-Khwarizmi invented that technique. He figured out that in Arabic text, certain letters appear way more frequently than others, and if you just count the letters carefully, you can use those frequency patterns to crack substitution ciphers. You're sitting in al-Khwarizmi's workshop, and he's showing you intercepted messages that look like gibberish. The Byzantines think they're so clever with their substitution ciphers, where every A becomes an X or whatever. But al-Khwarizmi just starts counting. He counts every single letter. He makes frequency tables. He's literally turning language into numbers, into patterns, into something measurable and therefore computable. This is data analysis. This is exactly what your spam filter does. This is what machine learning does. He's building a systematic procedure for finding patterns in information. Every time your bank flags a suspicious transaction based on unusual patterns, it's using principles that al-Khwarizmi figured out while breaking codes. Then there's al-Jazari, and oh man, if this guy had been born today, he would have a YouTube channel with 50 million subscribers. Born in 1136, he was an engineer who built actual programmable machines. Not computers exactly, but automata, which are mechanical devices that could follow a sequence of instructions with amazing precision. He built a programmable humanoid robot band that could play music. You heard that right. Programmable robot band. In the 12th century, the musicians could be programmed to play different rhythms and melodies and patterns. Think about that concept for a second. Programmable instruments. You change the mechanism and they play different music. It's the exact same concept as changing your code to get different behavior from a computer. You watch him work on his absolute masterpiece, an elephant clock. It's not just a timepiece that tells you when it's 3 o'clock. It's a full automated show. Every half hour, mechanical birds start chirping. Doors open, figures move through precise sequences. Musicians play. It's basically medieval animatronics. But here's the absolutely brilliant part that makes my brain hurt. It's all programmable. Al-Jazari can change what happens and when it happens by adjusting the internal mechanisms. He's literally writing programs in gears and water flow and mechanical linkages. The concept of stored instructions, of sequences that can be programmed and executed automatically. Your boy al-Jazari was doing it 800 years ago with pulleys and weights instead of silicon chips. Now let's talk about the Banu Musa brothers, because these three Persian scholars were like the Wright brothers, except they invented automation instead of airplanes. They wrote a legendary book called the Book of Ingenious Devices. Sounds like something from a fantasy novel, right? It's a massive collection of detailed blueprints for 100 mechanical devices, and many of them are programmable. They created automatic flute players, where you could change the melody by adjusting the mechanical mechanism. They built self-operating fountains. They built automated tea dispensers that could pour different amounts of tea based on how you programmed the mechanism. They were programming machines 800 years before Charles Babbage even existed. But my personal favorite scholar has to be al-Haytham, also known by his Latinized name al-Haytham, and this dude was certifiably obsessed with understanding light. He literally locked himself in a dark room for years to study how light works and how eyes perceive light. He was basically the medieval equivalent of someone who locks themselves in a lab for years to study one specific thing. But here's the important part. He didn't just observe light, he turned observation into algorithm. He developed what we now call the scientific method as a formal procedure. Make a hypothesis, run an experiment, collect data, analyze the data, draw a conclusion, then repeat the whole process. That loop, that iterative process, that's an algorithm for discovering truth. That's exactly how machine learning works. You have a model. You test it. You measure how accurate it is. You adjust it. You test again. That's al-Haytham's legacy. You're in al-Haytham's darkened chamber in Cairo, and he's showing you light bending through water and glass, creating patterns on the wall. He's not just pointing and saying, "Wow, that's cool." He's measuring everything. He's calculating angles. He's predicting what will happen if he adjusts the water. He's turning the behavior of physical light into mathematical rules, and then testing whether those rules actually work. When your phone's camera corrects for lens distortion automatically, it's using optical principles that al-Haytham worked out in the 11th century. When VR headsets track your eye movement with incredible precision, they're using theories of vision that he developed while Europe was in what they call the Dark Ages. Here's something that will legitimately mess with your head. These medieval scholars weren't just inventing the tools of computation. They were thinking algorithmically about thinking itself. Al-Farabi, a philosopher working in Damascus, decided to take human reasoning itself and break it down into logical steps. He created flowcharts for arguments, actual flowcharts, with decision points and branches, just like a medieval version of a PowerPoint presentation. If premise A is true, then proceed to conclusion B. But if premise A is false or doubtful, then check premise C instead. That's an if-then-else statement. That's the foundation of every single programming language that's ever been written. He was writing pseudocode in the 10th century. You sit in on one of his lectures, and it's genuinely eerie how modern it feels. He's drawing diagrams on a board, showing how thoughts connect, how one idea leads logically to another idea, how conclusions must follow from premises if the reasoning is sound. He's debugging human reasoning like it's a computer program. He's finding logical errors and fixing them. When modern computers use Boolean logic, those true-false, yes-no, 1-0 binary decisions that literally everything digital depends on, they're using logical structures that Islamic philosophers mapped out while trying to understand how God's creation thinks. But maybe the real superstar might be al-Tusi, working in the 13th century in Persia. This polymath didn't just study mathematics like it was a hobby. He fundamentally revolutionized how we think about mathematical modeling. He created geometric models that could predict where planets would be in the sky with incredible accuracy. But here's the thing that makes this relevant to algorithms. His models were essentially algorithms for computing celestial positions. You input a date and follow his geometric procedures step by step, and out comes the location of Jupiter or Mars or Saturn. It's a function just like any function in a modern programming language. Input goes in, procedure happens, output comes out. You're in his observatory in Mariga, surrounded by massive brass instruments that measure angles and distances, but the real computers are the human calculators working at tables, following al-Tusi's procedures precisely step by step, turning observations of the sky into predictions for the future. They're running algorithms with pen and paper and tables of numbers, creating astronomical tables that sailors would use to navigate the oceans for centuries. Every GPS satellite orbiting Earth right now, every calculation that tells you exactly where you are and how to get where you want to go, uses mathematical techniques that al-Tusi and his team developed in medieval Persia. Your phone can tell you you're standing on 5th Avenue and 42nd Street because of a 13th century Persian mathematician. Then there's Ibn al-Shatir, a 14th century timekeeper at the Umayyad Mosque in Damascus. This guy was obsessed with precision in a way that seems almost neurotic. He didn't just want to know what time it was, he wanted to know exactly what time it was down to the minute, because the call to prayer depends on it. So he developed mathematical models that could account for every tiny variation in the sun's apparent motion as it moves across the sky throughout the year. His calculations were so precise that Copernicus, the famous astronomer who revolutionized our understanding of the solar system, basically copied his equations almost word for word. Ibn al-Shatir was so accurate that his models worked centuries later. You watch Ibn al-Shatir at work, and it's like watching a human computer. He has tables of numbers, he has correction factors, he has adjustment procedures. He's built an entire computational system for timekeeping. When your phone automatically adjusts for daylight saving time, when it syncs with atomic clocks in space to give you the exact time, it's following in the footsteps of a Damascus mosque keeper who just wanted to make sure everyone prayed at exactly the right moment. The infrastructure of global timekeeping that makes modern civilization possible traces back to his work. Now here's what really gets me about this whole era. These scholars weren't hoarding knowledge. They shared everything. They wrote detailed commentaries on each other's work. They sent letters across thousands of miles arguing about mathematical proofs. They created a peer-to-peer network of intelligence where each node was improving and expanding on the other's discoveries. It was open source software development 800 years before computers existed. While European knowledge was being locked away in monasteries and guarded jealously, Islamic scholars were creating the world's first information superhighway, and they were all actively contributing to it. Alright, let's get down to the really practical stuff, because all this historical context is cool. But you probably want to know what these medieval people actually did that your laptop is doing right now. Let me show you how a 1200-year-old algorithm is literally running on your computer as we speak. Buckle up, because this is where it gets genuinely weird and fascinating. You open Excel, type in some numbers, click sum, and boom, you get an instant total. Feels like magic, right? Now let's go back to Baghdad. You're a merchant and a caravan just arrived from Damascus. You made 1247 dinars from selling silk. You made 892 dinars from spices. You made 445 dinars from manuscripts. But you owe 387 dinars in taxes and business expenses. You need to know your profit right now. In Europe, they're still using Roman numerals. Try adding MCCX LV7 to DCCX EPCI to CDX LV, and then subtracting CCCLXX V7. Go ahead. Seriously, I'll wait. Actually no, we'll be here forever, so let's not do that. But you're in the Islamic world in the 9th century, baby. You've got something way better than Roman numerals. You've got Hindu Arabic numerals, which are absolutely revolutionary. More importantly, you've got algorithmic procedures for actually doing arithmetic with them. Al-Khwarizmi didn't just introduce these numerals to the Islamic world like he was showing off a cool new gadget. He wrote actual step-by-step guides for using them. Place value, carrying over when a column adds up to more than 9. Borrowing when you need to subtract and don't have enough. All those elementary school nightmares were his systematic innovations. He literally wrote the user manual for arithmetic. You're sitting in a counting house watching a professional scribe work through al-Khwarizmi's method. First, align your numbers by place value. Add the ones column. Get 24. That's more than 9, so write down 4 and carry the 2. Move to the tens column and add those numbers plus the carried 2. Get 12. Write down 2 and carry the 1. Move to the hundreds column, and so on. It's so mechanical, so systematic, so repeatable that you could teach it to a child, or fast forward to the 20th century, to a machine. Every time your computer adds 2 numbers, it's following al-Khwarizmi's algorithm, just running at 3 billion times per second using electrons instead of ink. But addition is baby stuff, and your computer does way more complex things. Let's talk about something your computer does billions of times per second without you even thinking about it. Solving equations. When you use GPS and it triangulates your position, that's solving multiple equations simultaneously to figure out exactly where you are. When Instagram applies a filter to your selfie and makes you look way better than you actually do, that's solving matrix equations for every single pixel in the image. When your credit score gets calculated, when your loan gets approved or denied, when Netflix figures out what show to recommend, equations are running in the background. Al-Khwarizmi invented the systematic method for solving quadratic equations, not just finding one answer. He created a procedure that always works regardless of the specific numbers. He breaks equations into 6 different types and provides a specific algorithm for each type. It's like he's writing a switch statement in code. If the equation looks like this pattern, do procedure A. Else if it looks like that pattern, do procedure B. Else if it looks like this third pattern, do procedure C. Your computer's equation solving libraries, the mathematical functions that power everything from engineering simulations to graphics rendering, are just faster automated versions of his methods. Now here's where it gets absolutely crazy and explains why machine learning and artificial intelligence work the way they do. You know how computers can find patterns in massive amounts of data. how they can predict what you want before you know you want it, how they can recognize your face in a photo, how they can generate images from text descriptions, pattern recognition and data analysis. The conceptual and mathematical foundation for all of that was laid by Islamic scholars studying linguistics and cryptography and astronomy. Al-Kindi's frequency analysis wasn't just for breaking secret codes and winning medieval espionage games. It was one of the first systematic approaches to pattern recognition. The procedure is simple: count the occurrences of every letter, calculate the frequencies, compare your frequencies to known patterns, draw a conclusion about what the message actually says. That's exactly what your spam filter does. It counts word frequencies in emails. It calculates what percentage of the email contains spam keywords. It compares the calculated frequencies to patterns from known spam emails. It makes a decision about whether to block it. Your email thinks like a 9th century cryptographer. You're watching Al-Kindi analyze a coded text, and his process is weirdly familiar if you understand modern programming. First, gather data. Count every occurrence of every letter. Second, organize the data into frequency tables. Third, identify patterns. Which letter combinations appear most often? Which trigrams and digrams show up repeatedly? Fourth, test hypotheses. If this is the pattern I think it is, then this coded message should decode to this specific plain text. Fifth, validate results. Does the decoded message actually make linguistic sense? That's the scientific method. That's machine learning. That's every data analysis algorithm ever written running on every server on the internet. Let me tell you about something that will absolutely bake your noodle. Medieval Islamic scholars invented recursive algorithms, which sounds really technical, but is actually kind of mind-bending when you think about it. A recursive algorithm is one where the solution involves solving a smaller version of the same problem. Like, to find the answer to a big problem, you solve a medium problem. To solve the medium problem, you solve a smaller problem. To solve the smaller problem, you solve an even smaller problem, until you reach a problem so small you can just solve it directly. Then you work backwards. Al-Khwarizmi was doing this with his mathematical methods. To solve a complex inheritance distribution problem, he breaks it into simpler subproblems, solves those, and combines the results. That's recursion. Every programmer reading this knows that recursion is incredibly powerful, but also incredibly easy to mess up. Medieval scholars were figuring out how to avoid infinite loops and stack overflows centuries before computers existed. They were thinking about the computational limits of their methods. They understood that some procedures would take forever if you weren't careful about how you set them up. Then there's optimization, which is another boring word for something actually fascinating. Your computer has limited resources: memory, processing power, time. So programmers need to figure out the most efficient way to solve a problem. Do it in a stupid way, and your entire operation grinds to a halt. Do it intelligently, and everything runs smooth. Islamic mathematicians were obsessed with optimization. When calculating astronomical positions, every second of computation mattered because human computers might spend hours on calculations. So they developed methods that used fewer steps, fewer operations, less time. They were literally writing optimized code using pencil and paper. You're sitting in an observatory, watching a calculator work through an astronomical problem using Al-Tusi's methods. She's following the procedure exactly. Each step is designed to minimize unnecessary work. Each calculation builds on the previous one efficiently. When a modern computer scientist talks about big O notation and algorithmic complexity, about whether a solution takes linear time or exponential time, they're wrestling with the same problem that Al-Tusi was wrestling with. How do we solve this faster? Here's another thing that medieval Islamic scholars figured out: that shapes every single app on your phone. Data structures. That's a fancy term for the way you organize information so you can actually use it. If you have a million numbers all jumbled up in a pile, finding a specific one takes forever. But if you organize those numbers in a specific way, like a sorted list, you can find any number super fast. If you organize them in a tree structure, you can make searching even faster. This matters because the difference between a slow app and a fast app is often just about how the data is structured. Islamic mathematicians developed sophisticated systems for organizing mathematical information, tables of trigonometric values organized so they could be found quickly, astronomical tables arranged so you could look up the position of a planet for any given date. Inheritance calculation tables structured to make finding relevant cases efficient. They weren't thinking about this consciously as data structure design, but that's exactly what they were doing. They were optimizing information access. They were creating the conceptual ancestors of databases. Now let's talk about error checking and validation, because this is huge and kind of boring until you realize how important it is. When you send money online, you don't want the wrong amount arriving at the wrong bank account, right? So there are checks built in, little algorithms that verify the data is correct before anything actually happens. Islamic mathematicians were obsessed with verification because a calculation error in an astronomical table could mess up navigation across the desert. One wrong digit could cause a caravan to get completely lost, so they developed procedures for checking their work. Cross-verification methods. Different ways of solving the same problem to see if you get the same answer. Systematic review processes. They were doing quality assurance in the 10th century. Every time your bank verifies your credit card number using that little checksum algorithm, it's using concepts that medieval Islamic scholars invented because they understood that human beings make mistakes and need systematic ways to catch them. But maybe the most important thing these scholars figured out was abstraction. That's a word that sounds complicated, but just means taking something specific and making it general. Like instead of solving the problem of dividing 17 camels 3 ways, you solve the general problem of dividing any number of things among any number of people. Once you have the general solution, you can apply it to specific cases. This is the foundation of all reusable code. When a programmer writes a function, they're creating an abstraction that can be used for many different purposes. Medieval Islamic mathematicians were doing exactly this. Al-Khwarizmi's procedures weren't just for inheritance disputes, they were for any problem that could be reduced to the same mathematical form. You're reading through his work and you start to see the pattern. He's not giving you 100 specific solutions to 100 specific problems. He's giving you a few general procedures that can be applied to thousands of different problems if you understand how to translate your specific case into the general form. That's genius. That's powerful. That's the foundation of software development. That's the reason that the same code on your computer can run on someone else's computer on the other side of the world with different hardware and different operating systems, because it's written at a level of abstraction that's independent of those specific details. You wake up on day 3, and something has shifted in your understanding. You're starting to realize that these medieval scholars weren't just figuring out math problems, they were literally building a model of how thinking works. They were creating a framework that would eventually let machines think, and that is absolutely terrifying and amazing at the same time. So let's talk about logic itself, because logic is where algorithms begin and where artificial intelligence lives today. Islamic philosophers and mathematicians developed formal systems of logic that went way beyond what Aristotle had done centuries before. They created rules for how arguments should work. They defined what made a proof valid. They figured out how to take a complex argument and break it down into simple steps. Each step had to follow logically from the previous ones. No hand-waving, no vague appeals to intuition, just pure logic. When you use a computer today, and it follows a chain of reasoning to reach a conclusion, it's following rules of logic that Islamic scholars formalized. Al-Farabi, in particular, was obsessed with logic. He created something called syllogistic logic, where you have major premises and minor premises, and then a conclusion that follows necessarily from those premises. If all humans are mortal, and if Socrates is human, then Socrates must be mortal. That seems obvious today, but he was formalizing the rules that make this work. He was creating a mechanical procedure for reasoning. You follow the rules and you get valid conclusions. If you break the rules, you don't. It's algorithmic thinking applied to human reasoning. You're reading through his logical texts, and it's eerie how similar they are to flowcharts. Decision points, yes, no branches, processes that happen if certain conditions are true. He's literally diagramming thought itself. When a programmer writes an if-then-else statement, they're using logical structures that al-Farabi mapped out. When a doctor's diagnostic software asks questions and narrows down possibilities, it's using his methods. When an AI chatbot responds to your input by reasoning through a series of logical rules, it's following principles he developed. But here's where it gets really mind-bending. Islamic scholars realized something crucial about logic. Logic could be reduced to symbols. You didn't need to write out full sentences. You could use abbreviations, symbols. If you represented everything as symbols and learned the rules for manipulating those symbols, you could do reasoning purely mechanically without needing to understand what the symbols actually meant. This is huge. This is the foundation of formal mathematics. This is why computers work. Ibn Sina, also known as Avicenna, took this further. He created a complex logical system where you could combine simple statements into complex ones. You could negate statements. You could create chains of implications. You could do logical operations that looked a lot like what happens in a computer when it manipulates ones and zeros. Boolean algebra, which is the foundation of all digital computers, is just a formalization of the kind of symbolic logic that Ibn Sina was working with. You're trying to follow one of his arguments, and it's dense, really dense. But what you start to see is that the meaning doesn't matter. You could replace every word with a symbol and just follow the rules mechanically. It would still work. This is the insight that eventually led to modern computing. If logic could be reduced to mechanical symbol manipulation, then machines could do logic, machines could reason, not because they understand anything, but because they're following rules. Now let's talk about the concept of proof, because this is also absolutely central to algorithms. A proof is a sequence of statements where each statement follows necessarily from previous statements and from accepted axioms. You start with what you know to be true. You apply logical rules. You reach a new conclusion. Then you use that conclusion, along with other facts, to reach an even more complex conclusion. Eventually you reach the statement you were trying to prove. Each step has to be correct, or the whole thing falls apart. This is exactly how an algorithm works. Each step follows from the previous one, according to specified rules. Islamic mathematicians became obsessed with proofs. They didn't just want answers. They wanted to know why something was true. They wanted to be able to verify it. They created systems for writing down proofs so clearly that anyone could check them. This was revolutionary. Before this, you could just claim something was true, and if you were smart enough, people might believe you. But now you had to prove it rigorously. Every step had to be justified. This is called mathematical rigor, and it's the foundation of all formal reasoning. You're watching a scholar construct a proof step by step. Assume X. If X, then Y follows from Rule 5. If y then z follows from rule 2, therefore z is true. Each step is marked with which rule justified it. If anyone doubts the conclusion, they can check every single step. This is what debugging means in programming. You follow the logical path the code is supposed to take and verify that each step is correct. If the output is wrong, you find the step where it went wrong and fix it. Medieval scholars were debugging mathematical proofs 800 years before programmers were debugging code. And here's something else that's absolutely crucial. Islamic scholars understood that different problems had different computational complexity. Some problems could be solved quickly, some required more steps. Some seemed incredibly hard. They didn't have the vocabulary to describe algorithmic complexity, but they understood the concept. A problem that requires multiplying two large numbers is significantly harder than a problem that requires adding two large numbers. A problem that requires checking every possible combination of elements grows exponentially harder as the number of elements increases. You're reading al-Khwarizmi's notes on solving different types of equations, and he actually comments on how some types are harder to solve than others. He's noticing that as the problem gets more complex, the algorithm takes more steps. This is the beginning of computational complexity theory. This is understanding that not all problems are created equal from a computational standpoint. Some problems that seem simple are actually easy to solve algorithmically. Some problems that seem complex are actually simple once you know the trick. This understanding shaped everything about how we approach computation today. Now let me talk about something wild that Islamic scholars figured out, but it took until the 1930s for mathematicians to fully formalize it. The concept of an effective procedure. An algorithm is a procedure that's mechanical, deterministic, and guaranteed to terminate. You can give it to someone with no special knowledge, and they can follow it and get the right answer. You can give it to a machine with no intelligence, and it will still work. This is what makes something an algorithm versus just a general approach. An algorithm is precise enough that a mindless entity could follow it. Islamic scholars understood this intuitively. When they wrote procedures for calculating things, they wrote them so clearly that a trained calculator could follow them without understanding mathematics. Just execute the steps. This meant their procedures were algorithmic in the modern sense. They were formal and mechanical and unambiguous. Al-Khwarizmi could hand his inheritance calculation procedure to a scribe with minimal mathematical training, and that scribe could correctly solve complex inheritance disputes just by following the steps. You're sitting in a counting house and a merchant is watching a young apprentice follow al-Khwarizmi's procedure to solve an inheritance problem. The apprentice has never studied algebra. He doesn't understand what the procedure is doing or why it works. He just follows the steps. Calculate this. Write it down. Carry this. Look up this value in the table, and somehow he gets the right answer. The merchant is amazed. You're amazed. You're both watching a human being execute an algorithm. This is the key insight that eventually made computers possible. If you can reduce a problem to a precise sequence of mechanical steps, then anything, human or machine, can solve that problem as long as they follow the steps correctly. It doesn't require intelligence. It doesn't require understanding. It just requires mechanical execution of instructions. This is what blew up the myth that thinking is uniquely human. Mechanical thinking is possible. Algorithmic thinking is possible. Now let's talk about the House of Wisdom's approach to error correction and validation, because this is actually where they got really sophisticated. When you have human computers working on astronomical calculations for hours, mistakes happen. So the Islamic scholars developed systematic procedures for checking work, double-checking, triple-checking sometimes. Different methods for solving the same problem to verify consistency. spot-checking samples of calculations, building redundancy into the system so that an error in one place would be caught because it contradicted something calculated elsewhere. You're in the astronomical department, and you see this in action. A human calculator finishes a complex calculation. Another calculator independently follows the same procedure to solve the same problem. If they get the same answer, it's probably correct. If they get different answers, they both go back and check their work step by step until they find the error. This is quality control. This is systems thinking. This is understanding that you can't just hope people won't make mistakes. You have to build verification into the process. Every time a bank verifies a transaction through multiple checks before processing it, every time a computer runs a verification algorithm to make sure data wasn't corrupted, every time a medical device runs diagnostic tests to make sure it's functioning correctly. That's the legacy of Islamic scholars who built error detection into their mathematical procedures. They understood that systematic procedures needed systematic verification, but maybe the most profound thing that Islamic scholars contributed to algorithmic thinking was the concept that knowledge itself could be systematized and transmitted. That's what the House of Wisdom was all about. Not just collecting knowledge, but organizing it so it could be understood and used by others, creating standardized notation, defining terms clearly, writing procedures down precisely, building libraries so knowledge could be accessed when needed. This is what enables science and technology to progress. Each generation doesn't have to start from zero. They can stand on the work of previous generations because that work has been systematized and documented. You're in the library section of the House of Wisdom and you're absolutely blown away. Books are organized by subject, cross-references connect related works, translations exist in multiple languages, so knowledge isn't locked into one linguistic community. Indexes allow you to find information quickly. This is information architecture. This is database design. This is understanding that the value of information isn't just in having it, but in being able to find it and use it efficiently. Modern computers with their hierarchical file systems and search algorithms and metadata are just sophisticated versions of what the House of Wisdom built on a physical scale. You wake up on day 4, and you're starting to understand that we're not just talking about individual mathematical discoveries. We're talking about a completely different way of thinking about the world. A way of thinking that eventually made the modern world possible. And it came from medieval Baghdad. So let's talk about how these algorithms and systematic procedures spread and evolved and eventually turned into the digital age we're living in. The knowledge from the House of Wisdom didn't stay in Baghdad. It spread, scholars traveled, books got copied and sent to libraries across the Islamic world and beyond. When Al-Andalus, that's Islamic Spain, became a major intellectual center in the 11th and 12th centuries, they weren't starting from scratch. They had texts from Baghdad, they had the accumulated knowledge of the House of Wisdom, and they built on it. Spanish Muslim scholars like al-Zarqali made improvements to astronomical calculations. They refined trigonometric tables. They created new mechanical devices. They were continuing the work that al-khwarizmi and al-Tusi had started. Then a really important thing happened. European scholars started translating Islamic texts. Gerard of Cremona in the 12th century translated over 100 texts from Arabic to Latin. Al-Khwarizmi's book on algebra got translated, and suddenly Europeans had access to algorithmic procedures. The word algorithm itself entered European languages. European mathematicians started learning these systematic methods. Slowly, very slowly, the algorithmic way of thinking started spreading beyond the Islamic world. But here's the thing. Europe didn't immediately understand why these procedures were so important. They knew them as tools for practical calculation. Merchants used algorithmic procedures for bookkeeping. Engineers used them for design and construction. But the deeper insight that the universe itself could be understood algorithmically, that took longer to develop, that's what led to modern science and modern computing. You're watching this knowledge transfer happen across centuries. A book travels from Baghdad to Cordoba. A scholar in Cordoba studies it and adds their own insights. The enhanced version gets translated to Latin. A European scholar learns from it. The European adds their own ideas. Hundreds of years later, centuries later, these ideas are reflected in the work of people like Descartes and Newton and Leibniz. It's a chain of transmission that goes back to medieval Baghdad. By the time you get to the 17th century, the systematic algorithmic approach had become normal in European science. Descartes developed analytical geometry by creating algorithms for translating geometric problems into algebraic ones. Newton developed calculus as a set of algorithmic procedures for analyzing rates of change. Leibniz improved on Newton's calculus and created notation that was even more algorithmic, easier to manipulate mechanically. These European mathematical titans were building on foundations laid by Islamic scholars centuries before. Then, in the 19th century, George Boole created Boolean algebra, a system for doing logic using symbols and mechanical operations. This is directly descended from the symbolic logic that Ibn Sina and other Islamic philosophers developed. Boolean algebra became the foundation of all digital computers because computers ultimately just manipulate ones and zeros using Boolean operations. And Boolean logic traces back to medieval Islamic philosophy. You're starting to see the chain. Islamic scholars developed systematic procedures for solving problems. They reduced these procedures to mechanical steps that didn't require understanding, just execution. They formalized logic into symbolic operations. These ideas eventually reached Europe. European mathematicians refined them and developed new branches of mathematics based on algorithmic thinking. Then, in the 20th century, people like Alan Turing and John von Neumann took these ideas and figured out how to make machines that could execute them. And that's how we got computers. But let me give you a specific example because this chain is abstract and I want to make it concrete. Al-khwarizmi's book on algebra got translated to Latin and became known as a text on algorithms. One of the key things it taught was how to solve linear equations systematically. Solving equations is about finding unknown values. You have constraints, relationships between known and unknown quantities. You manipulate the equation according to rules until the unknown is isolated and you can read off the answer. Then mathematicians realized you could do this with many equations at the same time. Systems of equations. If you have multiple unknowns and multiple constraints, you can solve for all the unknowns using systematic procedures. This got formalized as matrix algebra and linear algebra. You represent the equations as matrices, numbers arranged in rows and columns, and then you apply algorithmic procedures to solve them. Every computer graphics system, every engineering simulation, every piece of artificial intelligence uses linear algebra. And linear algebra is just a sophisticated version of al-khwarizmi's equation-solving procedures. Your phone can recognize your face by comparing it to a database of faces using linear algebra. Self-driving cars use linear algebra to understand what the camera sees. ChatGPT uses linear algebra in every single forward pass through the neural network. All of it traces back to an algorithm that was developed in 9th century Baghdad to solve equations. Now let me blow your mind with how this worked out in the 20th century. Alan Turing was a mathematician who had a really important question. What does it mean for something to be computable? Is there a limit to what machines could theoretically compute if given enough time and resources? He answered this by imagining a machine, now called a Turing machine, that could follow algorithmic procedures. It had a tape of symbols, a head that could read and write symbols, a set of rules that told it what to do based on what symbol it saw. And he proved that this simple machine could compute anything that was computable at all. Why is that important? Because Turing proved that algorithms were the fundamental nature of computation. If you could express a procedure as an algorithm, then a machine could execute it. This is the theoretical foundation of every computer on Earth. And you know what Turing was drawing on? The concept of an algorithm that goes back to al-khwarizmi. The idea that complex problems could be reduced to sequences of simple mechanical steps. Turing was formalizing this concept and proving its power. You're reading Turing's papers, and you keep seeing references to previous mathematicians and logicians. Their shoulders were all standing on shoulders that went back centuries. And somewhere in that chain is al-Khwarizmi working out how to divide camels fairly. It's wild. The theoretical foundation of modern computing is an unbroken chain that goes back to 9th century Baghdad. Then John von Neumann took these ideas about what machines could theoretically compute and figured out how to actually build them. He designed the basic architecture that almost every computer still follows today. You have memory where data is stored. You have a processor that executes instructions. You have a way of moving data between memory and processor. Instructions come from memory. Data comes from memory. The processor executes instructions step by step, and each instruction modifies the data or moves data around. It's algorithmic execution at the hardware level. Von Neumann was trained in logic and mathematics. He understood the theoretical work of Turing and Church and Gödel. He understood that algorithms were fundamental. So when he designed a computer architecture, he designed it to execute algorithms. And that architecture became the standard. Most computers follow the von Neumann architecture. Phones follow it. Laptops follow it. Servers follow it. Your entire digital life is built on top of a computer architecture designed by someone drawing on a theoretical foundation established by Turing, who was drawing on the concept of algorithms that goes back to al-Khwarizmi. So when you pick up your phone and it does something amazing, any amazing thing you can think of, that's ultimately possible, because medieval Islamic scholars figured out how to reduce complex problems into sequences of simple steps. They created a framework for thinking about computation centuries before computers existed. They proved that systematic procedures could solve problems that otherwise seemed intractable. They showed that the same procedures could be applied to different specific cases. They created the foundation. You're sitting in a modern data center with the hum of thousands of computers around you, processing trillions of operations per second, and you realize it's all built on foundations laid 1,000 years ago. These machines are executing algorithms. Millions of algorithms. Billions of algorithms. Every process, every operation, every instruction can be traced back to the concept that al-Khwarizmi pioneered. And that concept came from trying to solve practical problems in medieval Baghdad. Here's something wild: cryptography. Every time you send a secure message online, when your bank transfer is encrypted, when your passwords are hashed, that's using algorithms. Modern encryption algorithms are incredibly complex, but they're fundamentally descended from Al-Kundi's work on frequency analysis. He figured out that patterns in language could be analyzed systematically. Modern cryptography takes that principle to an extreme. It finds patterns and creates algorithms that hide those patterns or create patterns that are computationally impractical to crack without the right key. Machine learning and artificial intelligence. This is the cutting edge today. Computers that can learn from data and make predictions. Neural networks that can recognize images and generate text. The whole AI revolution. And yet the fundamental algorithms that power all of this, the linear algebra, the optimization procedures, the error correction, the systematic verification, these all trace back to Islamic mathematics. The optimization algorithms used in machine learning are descendants of procedures developed to minimize computational effort in astronomical calculations. You're watching an AI generate text, and with each token it produces, it's running through matrix multiplications and activation functions, calculations rooted in linear algebra, which is rooted in equation solving, which goes back to al-khwarizmi. It's a continuous unbroken chain, from a Persian mathematician trying to figure out fair inheritance distribution to an artificial intelligence predicting what you want to say next. The systematic approach, the reduction of complex problems to simple steps, the mechanical execution of procedures, the verification and error correction, the organization and transmission of knowledge. These fundamental principles that came from medieval Islamic scholarship are still the foundation of how we build computers and software. We haven't moved beyond these ideas. We've just gotten better at executing them faster. You wake up on the last day of your journey back through time and history, and you're experiencing something profound. You've spent days understanding how medieval Islamic scholars accidentally invented the foundation of the digital age. You've traced the continuous line from al-khwarizmi to your smartphone. You've seen how systematic thinking, algorithmic procedures, and the reduction of complex problems into mechanical steps didn't just change mathematics, they changed human civilization. They made the modern world possible. Now let's talk about what this means for where we're going, because here's the thing that really matters. We're at a moment in history where artificial intelligence and machine learning and automation are transforming everything. Jobs are changing, industries are disrupting, the nature of work is shifting, and most people don't understand the fundamental principles underlying all of this. They think AI is magic, they think algorithms are mysterious, they think computers are incomprehensibly complex, but they're not. They're just executing procedures that were invented to solve practical problems 1,000 years ago in Baghdad. Once you understand that your phone is ultimately following algorithmic procedures, once you understand that AI is just mathematical optimization, once you understand that the entire digital revolution is based on medieval Islamic mathematics, something shifts. You realize that these aren't incomprehensible forces. They're tools, sophisticated tools, yes, but tools nonetheless. And tools can be understood. Tools can be controlled. Tools can be used wisely or foolishly. You're back in Baghdad one last time, standing in the House of Wisdom, and you're thinking about what these scholars would think if they could see what their work became. They'd probably be amazed and terrified. Amazed that procedures they developed for practical calculations led to machines that could execute trillions of operations per second. Terrified that those same procedures could be weaponized, that the algorithms they created could be used for surveillance, for manipulation, for control. Because algorithms are neutral, they're tools. What matters is how they're used. That's something crucial to understand. Al-Khwarizmi didn't invent algorithms and think about whether they'd be used for good or bad purposes. He was solving a problem. The algorithm is what it is. What matters is the implementation. What matters is the intent. What matters is what humans decide to do with these tools. The same algorithm that could help you find information online can also be used to spread misinformation. The same AI that can diagnose diseases can be trained to discriminate. The same cryptographic algorithm that protects your privacy can be used to hide illegal activity. This is why understanding where these technologies come from matters. It's not just trivia. It's the difference between being a passive consumer of technology and being an active participant in shaping it. If you understand that algorithms are based on medieval mathematics, If you understand that they're ultimately just systematic procedures, then you understand that they can be redesigned, they can be improved, they can be made more transparent and fair. They're not inevitable. They're choices. You're thinking about the House of Wisdom and how it worked. Scholars debated, they disagreed about approaches, different people proposed different solutions, the knowledge was shared openly, everyone could contribute. And this collaborative approach, this open exchange of ideas, this systematic verification and improvement through community review, this is what we need today. Not secretive algorithms developed behind closed corporate doors, not AI systems trained in ways we can't understand, not black box systems that make decisions affecting millions of people without transparency. We need the spirit of the House of Wisdom applied to modern technology. We need algorithmic transparency. We need to understand how the systems we depend on actually work. We need diverse perspectives shaping the development of AI. We need systematic verification and testing. We need error correction and accountability. We need to think like medieval Islamic scholars who understood that procedures should be clear enough that anyone could follow them. We should understand the algorithms shaping our lives. Here's something that will make you feel simultaneously empowered and slightly terrified. Every algorithm running on Earth, every piece of AI, every computer operation is ultimately following rules that humans created. The rules might be complex, they might be difficult to trace, but humans made them. Humans can modify them. Humans can improve them or replace them. You're not subject to incomprehensible forces. You're subject to the choices humans made, which means different choices are possible. The future is not determined. It's being written right now. Let me bring this back to something practical and personal. The skills that medieval Islamic scholars were really developing underneath all the mathematics and astronomy were problem-solving skills. Breaking down complex problems into manageable pieces, finding patterns, creating systematic approaches, testing solutions, refining based on results. These skills matter today more than ever. Whether you're dealing with a personal problem, a professional challenge, or a societal issue, the algorithmic approach works. Identify the problem, break it into steps, execute the steps systematically, verify the results, refine the approach, repeat. You can apply this to anything. If you're learning something new, break it into small pieces. Each piece is a simple step. Master each step. Combine them together. If you're trying to solve a problem at work, define what you're trying to achieve. Outline the steps needed. Execute each step carefully. Check the results. Iterate. If you're trying to understand a complex topic, break it down. Find the fundamental principles. Build from simple to complex. This is what al-khwarizmi was doing. This is what works. But there's something else that's equally important that medieval Islamic scholars understood: the value of systematic documentation and knowledge sharing. Al-Khwarizmi didn't just develop algorithms and keep them secret. He wrote them down clearly. Other scholars built on his work, improved it, extended it, shared their improvements. This culture of open documentation and collaborative improvement is what accelerated progress. It's what moved mathematics forward. It's what eventually made computers possible, and we need more of this today. One of the biggest problems with modern technology is that it's often a black box. You don't understand how your phone works. You don't understand how algorithms rank search results. You don't understand how your data is being used. This lack of transparency is a departure from the spirit of the House of Wisdom. Medieval scholars believed knowledge should be documented and available. They believed other scholars should be able to review and improve the work. They believed the procedure was more important than the final answer because the procedure could be reused and improved. Imaging if modern AI systems were developed with the same transparency, if we could see the algorithms, understand the training data, review the logic, suggest improvements. This would require a fundamental shift in how technology companies operate. It would require making algorithms open source in ways they currently aren't. It would require regulatory structures that enforce transparency. It would be difficult and controversial, but it's how the House of Wisdom worked, and look at the progress they made. You're standing in that medieval library one last time, and you're thinking about what progress is. Progress isn't just about making things faster or shinier, it's about collective understanding. It's about building knowledge systematically, where each generation stands on the shoulders of the previous generation. It's about sharing techniques and procedures so others can benefit from them. The House of Wisdom understood this. They created progress through systematic sharing and collaborative improvement. We need to remember that as we build the future. Here's my challenge for you. Think about the technology you use every day. Your phone, your computer, your streaming services, your social media. None of it would be possible without algorithms, procedures, systematic operations that reduce complex problems into simple steps that machines can execute. And those procedures trace back directly to medieval Islamic mathematics, directly to al-khwarizmi and al-Kindi and al-Tusi and their colleagues at the House of Wisdom. They didn't know what they were starting. They just knew they had problems to solve and procedures that could solve them. That's it. That's all innovation really is. So what's the biggest takeaway here? First, that ancient knowledge is still relevant. That ideas developed 1,000 years ago are still the foundation of cutting-edge technology. Second, that systematic thinking works. That breaking problems into steps and executing those steps carefully and verifying results is powerful. Third, that transparency and collaboration lead to better outcomes than secrecy and competition. And fourth, that the future is not predetermined. It's being built right now through the choices we make about how to use these tools. Think about a moment the next time you unlock your phone with your face. Your phone is doing mathematical operations based on principles developed in medieval Baghdad. It's using linear algebra derived from equation-solving algorithms. It's using error correction methods inspired by medieval astronomers. It's using all of this at billions of operations per second and doing it so smoothly you don't even think about it. That's the power of systematic thinking. That's the inheritance from Islamic Golden Age scholars. The question you should be asking now is what comes next? What problems are we trying to solve today? What systematic procedures could help us solve them? What knowledge needs to be documented and shared? How do we create our own house of wisdom where brilliant people from different backgrounds collaborate on important problems and share their solutions openly? Because that's the real legacy of medieval Islamic scholars, not just the mathematics, not just the algorithms, but the approach, the commitment to understanding, to systematizing knowledge, to sharing it, to building on it together. You're back in the present day, and everything has changed. You can't look at technology the same way anymore. It's not magic. It's not incomprehensible. It's not the inevitable march of progress outside human control. It's tools, built on principles developed by people just like you trying to solve practical problems. And those tools can be guided, shaped, improved, redesigned by us, by people who understand where they came from and what they're really made of. And that's the real gift that medieval Islamic scholars left us. Not just algorithms, but the understanding that systematic thinking and collaborative knowledge can solve any problem we can imagine.